I am Aditi Rajpal, and today we shall be discussing chapter 1, which is real numbers. So what are real numbers? It's a collection of all rational and irrational numbers. Rational numbers are those which can be expressed in the form of a fraction, and irrational numbers are those which cannot be written in the form of fractions. Rational numbers consist of natural numbers which start from 1 and go on like 2, 3, 4, etc. Then we have whole numbers which start from 0 and then proceed like natural numbers. So examples would include 0, 1, 2, 3, etc. Then we have integers which could be both positive as well as negative. So it could be like 1, 2, 3, 4, or it could also be like -1, -2, -3. Then we have rational numbers which I just stated can be written in the form of p by q, that is a fraction. So examples of rational numbers would include 2 by 3, 3 by 5 and so on. And then we have irrational numbers which we cannot write in the form of fractions, and examples are square root of 2, square root of 3, square root of 5, etc. And together all of them give us these real numbers. Now we shall discuss Euclid's division lemma. So what does a lemma mean in mathematics? It refers to an already proven statement which is now being used to prove another statement. So this lemma was given by a Greek mathematician, Euclid, who is also often referred as the father of geometry, and he gave this lemma for division. So what it says is that if you are given any two positive integers, a and b, then there exist unique integers q and r such that a is equal to bq plus r. Now here a and b are your positive integers, q and r are some integers where q and r both can be equal to 0, but there's an additional condition on r that it can be greater than or equal to 0, but it has to be less than b. Okay, so we'll understand this by means of an example. So if I give you two positive integers 2 and 5, then if I do 5 divided by 2, I'll do that by long division. So I will get 2 2s are 4 minus 1. So this is basically your dividend. This over here is your divisor. And this you all must be knowing is called the quotient. And this is called the remainder. So Euclid's division is nothing but dividend is equal to divisor into quotient plus remainder. So here 5 is equal to divisor 2 into quotient 2 plus remainder 1. So in a way this is your a and b, and this is q, this is r. So essentially q and r are nothing but your quotient and remainder. So you just need to remember these two things over here, and an easy way to remember is through this, that dividend is equal to divisor into quotient plus remainder. Then we have Euclid's division algorithm. Now we just saw the lemma, and now we have the algorithm. Algorithm refers to a sequence of steps which are not random but well defined, and they are used to solve a particular problem in any subject, like in this case mathematics. So Euclid's division algorithm is used to solve the problem of finding the HCF of two given positive integers. Now what does HCF mean? HCF means highest common factor. Now its full form itself will tell you what it exactly is, okay? So if I give you any two positive integers, say 12 and 15, now what are the factors of 12? Factors of 12 can be like 2, we can have 3, what else? 2 3s are 6, and then you have another 2. For 15 it is 5 into 3. You can also have 1 as a factor. So these are the factors of 12 and 15. So the factor part is done. Then we have to look for the common factor. So here the common factors are 3 and 1, 3 and 1. So you have to choose the highest factor out of 3 and 1 would be 3. Hence HCF of 12 and 15 is equal to 3. So without even looking at the definition, we could figure out what HCF means. Okay, so just break it word by word. So you look at the factor, you look for the common factors, and then you choose the one which is the highest in value. So HCF of any two positive integers a and b is the largest positive integer d that will divide both a and b. Okay, largest, so highest, divides both a and b is common, and something that divides is nothing but a factor. Then we have certain steps which are involved in Euclid's division algorithm. So if you are given two positive integers c and d, you have to first figure out which integer is greater. So if c is greater than d, you apply Euclid's division lemma to them. So there will be two unique integers q and r such that c is equal to dq plus r, where r has to be greater than or equal to 0 but less than d. Alright, now your work doesn't finish at this stage, because now you need to see if your remainder is equal to 0 or if it is not equal to 0. If it is equal to 0, then you are done. D will be the HCF of C and D. If not, then you will again apply Euclid's division lemma, but this time to D and R. And you'll keep on performing these steps. You'll keep on applying Euclid's division lemma to essentially your divisor and your remainder until you get a remainder equal to 0. At that stage, whatever divisor you were having, that would become the HCF of C and D. So for example, if I give you 2 and 5, which is the bigger integer? 5. So 5 is greater than 2. I'll do a long division such that 2 is dividing 5. So 2 2's are 4 minus 1. So on applying Euclid's division lemma to 5 and 2, I can say 5 is equal to 2 into 2 plus 1, and clearly my remainder is not equal to 0. So what do? I again apply Euclid's division lemma, but this time to my divisor and to the remainder. So to 2 and 1. So again you perform this long division. So you will have 1 and you will have 2 over here. So 1 1's are 2 and you are left with 1. So this time I can write my 2 dividend as divisor 1 into quotient 1 plus remainder. Again, my remainder is not equal to 0. So I'll again apply Euclid's division lemma, but to 1 and 1 this time. Okay. So 1 divided by 1. So 1 1's are 1 and here you get 0. So now I'll write my 1 is equal to 1 into 1 plus 0. Now the remainder is equal to 0. So this 1 will become, the divisor over here becomes my HCF. Of what? Of the initial integers 2 and 5. So the HCF of 2 and 5 is equal to 1. Okay. Now we'll have some more examples to understand this. So you've been given these two positive integers. What you need to do first is you need to figure out which one is greater. So clearly 1, 2, 5, 6, 7 is greater than 4, 0, 5, 2. So you will perform a long division of 1, 2, 5, 6, 7 by 4, 0, 5, 2. So let's do that. So here if I get a 3, this will become 1, 2, 1, 5, 6. This will become 420. So I've applied my Euclid's division lemma to the initial integers, and I see that I get 1, 2, 5, 6, 7, which is my dividend, is equal to divisor into quotient plus remainder. This remainder is not equal to 0. So this time I'll apply my lemma to 4052 and 420. So you do this. Here I'll get a 9 and here we get 3780. Here you get 272. So on applying lemma to these integers, we get 4052 is equal to 420 into 9 plus 272. Again this remainder is not equal to 0. So we apply the lemma to 420 and 272. So in a similar manner, every time you keep on performing long division, and this time if you do it, you will get 420 equal to 272 into 1 plus 148. Again it is not 0. So apply the lemma to these two integers. So you will get 272 is equal to 148 into 1 plus 24. Again not 0, so apply it to 148 and to 24. So 148 is equal to 124 into 5. No, it will be into 1 actually when you solve it, plus 24. Okay. So again what we see here is that this remainder is not equal to 0. So you do 124 divided by 24 to get Euclid's division lemma result, and you will see that 124 is equal to 24 into 5 plus 4. Again, not 0, so this is a lengthy process, but you'll get your HCF, don't worry. So then apply the lemma to 24 and to 4. So you'll get 24 is equal to 4 into 6, and this time you get a 0. Now if your remainder is equal to 0, whatever divisor you were having, that becomes your HCF. So 4 in this case becomes the HCF of the two integers 4052 and 12567. Then we have a proving question. Show that every positive integer is of the form 2q and every positive odd integer is of the form 2q plus 1, where q is some integer. So again, we don't know what that integer is. So let a be a positive integer. Right now we are not commenting on its nature as to if it's even or odd. All we are saying is let a be a positive integer. And since I want this 2 over here, so I'll take b equal to 2. I have to take two unique integers. I have to take two positive integers a and b, and then we'll get two unique integers q and r by Euclid's division lemma. So we can apply Euclid's division lemma to them. Okay, so applying Euclid's division lemma to a and b, we get a is equal to 2 q plus r, where q and r are some unique integers such that r is greater than equal to 0 but less than b, which in this case is 2. Therefore, r can be equal to 0 or 1 but not 2, because here we do not see an equal to sign. So if r is equal to 0, we get a is equal to 2q. You simply substitute this value of r in this equation. Okay, and if r is equal to 1, we get a equal to 2q plus 1. That's it, hence proved. Because for every positive integer a, if it's even, it is of the form 2q. How can we say this is even? Because it is a multiple of 2. And if this is even, if I add 1 to this, this becomes odd, and that is what it says in the next line, that every positive odd integer, say a, is of the form 2q plus 1. So all you have to do is just assume this to be a and take b to be equal to 2 and just apply the lemma to get the results. So this is a similar question. So again, let's assume a to be a positive integer, and here we are having 4, 4, so let me take b equal to 4. Apply Euclid's division lemma to a and b, and you will get a is equal to 4q plus r, where q and r are some unique integers to a and 4, where r is greater than equal to 0 but less than b, which is 4. So r can be equal to 0, 1, 2 and 3 but not equal to 4, because it is less than 4 and not equal to. So again, if r is equal to 0, you substitute your value of r in this equation, you get a is equal to 4q. If r is equal to 1, we get a is equal to 4q plus 1. If r is equal to 2, a is equal to 4q plus 2. If r is equal to 3, we get a is equal to 4q plus 3. Now 4 we can write as 2 into 2q, and here this 4q plus 2 is from this expression we can take a 2 common. So we'll get 2 into 2q plus 1. So if I'm having any multiple of 2, it is always going to be even. So this is even, this is even. But look at the question carefully. It says you have to get the results for the odd integer. So we are not looking at this, we are just looking at the odd values, which are 4q plus 1 and 4q plus 3. And hence, looking at these two, say equations 1 and 2, we have proved that for any positive odd integer a, it is going to be of the form 4q plus 1 or 4q plus 3. Now we have a mouth-watering question. So here we are talking about sweets. So there are 420 Kaju burfis and there are 130 Badam burfis. So there's a sweet seller who wants to stack them in such a way that they take up the least area of the tray. And how many of such burfis can you place in each stack for this purpose? So this is indirectly asking you for the HCF. Now HCF of what? 130 and 420. So we'll make use of Euclid's division algorithm to find that. So 420 and 130. Which is the bigger integer? 420. So obviously we'll do 420 divided by 130. If I do that, I'll get a 3 here, 390 over here, and we'll get 30. So on applying the lemma, we get dividend is equal to divisor into quotient plus remainder. As you can see, this remainder is not equal to 0. So we'll apply this lemma again, but this time to 130 and 30. So again, you can perform this long division. I'm straight away writing the results. So you will get 130 is equal to 30 into 4 plus 10. Again, the remainder is not equal to 0. So apply the lemma to 30 and 10. And this time you will get 30 is equal to 10 into 3 plus 0. Since the remainder is 0, therefore whatever divisor I am having, which is 10 in this case, becomes my HCF. So HCF of 420 and 130 is 10. So the number of Kaju burfis and Badam burfis which can be placed together in each stack for this purpose would be how many? 10. So your answer is 10. Okay. Then we move on to a very important thing, which is the fundamental theorem of arithmetic. So it's interesting to see who gave this theorem, because this is of great importance. So this theorem was given by Carl Gauss, and this theorem was given in the year 1801. So it's very interesting to note that Carl Gauss was a child prodigy. Prodigy means he was very intelligent in a particular skill, and in that case he was very good at mathematics. So at the tender age of 3, he could help his father calculate his finances. So he gave this fundamental theorem of arithmetic, which applies to composite numbers. Now composite numbers are the complete opposite of your prime numbers. So prime numbers are those which can only be divided by 1 or by themselves. Composite numbers are those which can have factors other than 1, themselves. Okay, they can have other factors as well. Okay, so for example, 4, 6, 9, 10. They're all composite numbers. Why? Because 4 can have a factor of 4. It can have a factor of 1. Okay, but apart from getting divided by itself or by 1, it has other factors as well, which is 2 and 2. Alright. Similarly, 6 can be divided by 6 and 1, but also by 2 and 3. So for such composite numbers, Carl Gauss said that we can write them as a product of prime numbers. But this product will be written in a very unique fashion. Unique how? We'll just see. So unique in the sense it has to be in ascending order. Okay. So let me take a generalized case. So let's say x is some composite number. According to this theorem, I can write it as a product of my prime numbers, say P1, P2, P3 going on till Pn. So all of them are prime numbers, and they have to be written in ascending order for the order to be unique. Okay, which means P1 has to be less than P2, and further on Pn minus 1 should be less than Pn. So the thing is that these prime numbers are not necessarily distinct, which means that some of them can be equal as well, like P1 and P2 can be equal. So in case of prime numbers which are same or common, we can combine them using exponents, powers or indices. So basically, if I say 4 is going to be written in the form of prime factors as 2 and 2, then instead of writing this twice, I can simply write it as 2 to the power 2. Okay, similarly, if I have 9, it is 3 into 3. I can write it as 3 square. 27 can be written as 3 cube, 8 can be written as 2 cube, and so on. So if I am given, say 15, 15 has these two prime factors 5 and 3. So which is the correct way to write it? 15 is equal to 5 into 3 or 15 is equal to 3 into 5. You have to make use of this fundamental theorem of arithmetic to address this question. So this is the correct way and this is the wrong way, because this is fine that you've written 15, a composite number, in terms of its prime factors, but the order has to be unique, which is that you have to write it in ascending order. The factors are to be listed in ascending order. So it should be 3 first and then 5 and not the other way around. Now we have an example over here. So you have been given a number 4 to the power n, where n is any natural number like 1, 2, 3, 4, etc. You have to check that is there any value of n for which 4 to the power n would end with the digit 0. So you know that if any number ends with the digit 0, it has to be divisible by 5. Okay, so if I give you 50, if I give you 60, if I give you 750, all of them are divisible by 5. All of them. Okay, the list is endless. So basically, for any digit or for any number ending with digit 0, it should be divisible by 5. Now we know that 5 is also a prime factor, so we can make use of fundamental theorem of arithmetic here. So 4 to the power n can be written as a product of its prime factors. What are the prime factors of 4? 2 and 2. This will become whole to the power n. Again, I can combine these primes as 2 to the power 2 whole to the power n. In this case, we can multiply these two, so we'll get 2 to the power 2n. But do you see any prime factor of 5? No. So using fundamental theorem of arithmetic, we do not see 4 to the power n to being expressed as a prime factor of 5. Okay, it's not having any prime factor 5. It's only having the prime factor 2. If it's not having the factor 5, it means 4 to the power n is not divisible by 5. It means that this does not end with 0. So there is no value of n for which 4 to the power n would end with the digit 0. Then find the LCM and HCF of 6 and 20 by prime factorization method. The prime factorization method is nothing but writing any number as a product of its prime numbers. Okay, so for 6, what are its prime factors? 2 and 3. Note the order in which I am writing using the fundamental theorem of arithmetic. Then 20 would be what? 20 has 2 into 10. 10 is 2 into 5. We cannot do it any further. So 20 can be written as 2 into 2 into 5. I can combine the primes and it will give me 2 to the power 2 into 5. Now whenever you are looking for HCF, which is the highest common factor, you look for the common factor. So in 6 and 20, 2 is the only common factor. Okay, so HCF clearly becomes equal to 2. Right? Then what is LCM? LCM stands for lowest common multiple. So here what you do is, you take the factors of both the numbers and you just multiply them. But if a factor is repeating in both the numbers, like in this case 2, you go with that factor which has a higher power. So in case of 6 and 20, the LCM should be 3 into 5. No competition for them. Now 2 to the power 2 and 2, you can't write it like, like this. No. You only have to write 1, 2. So you choose the one with the higher power. So we choose 2 to the power 2. So 3 5s are 15, 2 to the power 2 is 4. So LCM becomes equal to 60. So this is how we found out the HCF and LCM using the prime factorization method. Now we have example 7, where we are given two integers 96 and 404. Once again, we have to find out their HCF using the prime factorization method. So 96, it is 2 into 48. 48 is 2 into 24. 24 is 2 into 12. 12 is 2 into 6. 6 is 2 into 3. You can't go further. So we can write 96 as 2. Now don't write it 2 into 2 into 2. You are in grade 10 now. Make use of exponents. So how many times this 2 is repeating? 1, 2, 3, 4, 5. So you can write it as 2 to the power 5 into 3 to the power 1. And similarly, let's find out the prime factors for 404. So we have 2, 202, 201, and then we can't go beyond 101. So 404 can be written as 2 to the power 2 into 101 to the power 1. We've written the prime factors. Now look for the common factors. 2's are the common factors in them. You have to choose the highest one. So that's going to be 2 to the power 2. So HCF of 96 and 404 is 2 to the power 2, which is equal to 4. Now you have to find out their LCM. Now you can obviously make use of the method that we used in the previous example, but here if hence is written, it means that you have to make use of the result which you got in the previous step to find out this. So how can I make use of my HCF to find out the LCM? So there is a result. It says that HCF into LCM is equal to the product of the two integers whose HCF and LCM you found out. and that is A into B. Okay, so HCF into LCM is equal to the product of the two integers. Okay, so using this, what we can do is that my HCF is what? 4. LCM we have to find out. The two integers are 96 and 404. So I can take my 4 down, so it will become 96 into 404 upon 4. Okay, and when you solve this, you get 101 over here. So LCM on solving will turn out to be 9696. Alright, so you have to remember this result. HCF into LCM is equal to A into B. Then you have to find out HCF of 6, 72 and 120. So 6 can be written as 2 into 3. 72. How can you write 72? 2, 36, 2, 18, 2, 9, 3, 3, 3, 1. So 2 is repeating 3 times and 3 is repeating 2 times. 120. How can we write 120? So 2, 60, 2, 30, 2, 15. And then you have 3, 5 and 5, 1. So 2 repeats 3 times. And then you have 3 to the power 1 and 5 to the power 1. You have to find out the HCF. So look for common factors. 2 and 3 are the only common factors here. So HCF is equal to 2 into 3 is equal to 6. So that is your answer. Okay.